Hello, everyone. I hope you all are holding up okay during finals. I'm just going to go through some example solutions for the latest exercise so that you all can look over them before the final. All right, so the first one was last. And so what I'm going to do is write down the cases in English that we want to convert into code, and then I'll go over writing some code, and then for a few of them I'll show some diagrams. But I really encourage you to go through and diagram any cases that you had trouble thinking through on your own before the final. I think that is a great exercise. Okay, so for last, the idea is if you had some linked lists like this. All right, so let's just imagine for a second that we were by hand trying to recursively find the last element of this list. So we know if we're given a linked list, right, that means, so if we had some variable list, it's pointing to this first node, right? And all we know about this node is what its current data is and if it has a next, okay? So when we're dealing with linked lists in these recursive functions, you should be thinking of it from thinking of what you would want to do from the perspective of a single node, because that's all that a single frame knows about, whether that node has a next and what that node's data is. And if it needs to know more about the rest of the list, you have to make a recursive call to go process that information. Okay, so let me undo that. So for last, the three cases are: one, our input is none. So in that case, we just return none. Okay, or another option is our next is none. And in that case, if the value of our node's next attribute is none, that means there's nothing after us. We must be the last node. Okay, so we are at the end. Okay, otherwise, this final case, if the input list is not none, our next is not none, that means we need to keep going towards the end. Okay, awesome. So let's convert this into some code. All right, so I already have all these functions set up, as well as the node class that you guys should have all had the starter code for. So for last, that first case, so I named the parameter LL for linked list. So if the linked list is none, then we return none. Okay. And then our second case, elif our next is none, that means that we're at the end. So let's return that data. Okay. Otherwise, we want to continue. So, okay, you could also write this in an else statement. So otherwise, we just want to continue towards the end, and we do this by making a recursive call to last, sending in our current linked list's next attribute. Okay, so why don't we go ahead and diagram a simple example of this? So we start out with main with an array of 51. I'll leave the RV until we actually return. And so here is where we would have 3 calls to the node constructor happening. So if you wanted to be complete about this diagram, you would see 3 frames to node init constructing this list, but I am just going to skip that for to keep this neat and concise. But what you would see if you followed those calls is so we start from the innermost function call, which is a call to the node constructor method. So first thing we do is create a node that has data. So I'm just going to say D and N. So data of 3. Next is none. And then we have a node whose data is 2. The next points here. And then up top, we have a node with data 1 and next points here. So when we call last, this first time, the return address is 39. The RV we don't know yet, but the linked list parameter is pointing here. Okay, so we check, is our linked list none? And it's not. So we check, is our next none? And it's not. And so then we recursively call last again. So we called it from line 49. RV we don't know yet, but now our LL parameter is pointing here. Okay, and so same thing. Is this none? No. Is our next none? No. So we're going to call last again. So RA is 49. RV we're not sure yet. Now LL is pointing here. And we check, is our linked list none? It's not, but is our next none? It is. So we hit a base case here and we return the data of our current node. So we return 3 in this frame. Okay, so now this frame is complete. So it returns to line 49. And line 49 was inside of this last function. So we look on our stack to find the most recently called last frame, and we know that this 3 value is being returned up there. And then we're done here. And now the return address again is 49, which is in our last frame. So we return 3 up there. And then lastly, we return this back up to main, but we didn't store it in a variable or anything. Like if we had done something like x equals last, then yeah, we would have an x up here that is 3. And then main returns and we get nothing back. So that is how you would diagram last. All right, the next function is value at. So we have some similar cases here. So we have one case where if the list is none, we know we want to return none here. Second case, if we are at desired index, return data. Otherwise, move closer to the desired index. Okay? So the way I like to think about this one is what's the easiest case for value at? The easiest case is you just want the first item in your list, because then you just return the data and you don't have to make any recursive calls. So this desired index is really 0, right? That's the time we don't have to keep checking the other elements in our list. So when we say move closer to the desired index, we're moving our index closer to 0. So let's take a look at this in code. All right, so taking a look at this one. So same thing, if the linked list is none, we want to return none. Otherwise, if our index is 0, that means we just want to return the data attribute of our current list. Otherwise, we need to keep moving closer to the desired index. So we recursively call value at the next attribute of our list. Since we've already checked the current data, we just want to keep looking forward and send in the index -1 to move it closer and closer to the base case. So imagine you were trying to find something at index 2, okay, so the third element. So the first time you'd call this, it would be you'd be looking at the 0th element, index would be 2. Second time, you'd be looking at the first element, but index would be 1. Third time, you're at the second element and index is now 0. You return the data of that element at the second index. And that was a mouthful. I definitely recommend diagramming this one out. All right, the next one is max. And I know this one caused a lot of trouble with the type checking. And that's just because the type checker expects you to be incredibly explicit about what the types of all of your variables are at each step, and it makes no assumptions based on your logic, even if you know it's supposed to be correct. So just so that you'll see that reflected in the solution I'm about to show you. So the first case, as always, if list is none, we return none. Okay, so secondly, we compare our current data versus the current max. And so then we update current max accordingly and process rest of list. Okay. All right, so let's take a look at some code for this one. All right, oops. So first we check if it's none, and as always, we return none in this case. Otherwise, we want to find, I'm just going to make a really long variable name here so it's very clear what this is doing. So max of rest of list is the result of calling our max recursively with our next attribute. So what this is going to do is going to call our function with the next attribute of the original list and find the maximum number of all the nodes that follow us. So imagine this with like a tiny example of something like 1, 2, 3. So if you imagine that we're starting out looking at 1 right here. So we know our data is 1, but we want to know what the max of the rest of our list is, okay? So we're going to just use our recursive function to just go compute that for us by just calling max again with the linked list's next attribute. So hopefully if our function ends up working as correctly expected, this will return 3 to us. So then in the final step, we just have to compare 1 and 3. Okay, so next, after we compute the max of the rest of our list, we check, is max of the rest of our list none? And if it is, then we know there's nothing after us, so we just return our own data. Okay, otherwise, if our data is greater than the max of the rest of the list, then we know we're the biggest value. Otherwise, we know that the max of the rest of the list is still going to be the winning value. Okay, so for this example that I drew, so let's see. So this will be 3, and then we check, is max of rest of list none? It's not. But is our data, which is 1, greater than 3? It's not. So then we jump down and return 3. So the max of this total list is 3. And I definitely recommend diagramming this one out as well. Right, the next one we had was linkify. So this one is a little different because we're given an actual list, not a linked list, as input. So instead of checking if our input list is none, we check if length of our input is 0, then we return none. Otherwise, create new node with current element of list and keep going. So, for example, if you had 1, 2, 3, the way you would imagine this function executing is first create a node with 1 as the data, then link it up to a node with 2 as the data, and then 3 as the data. All right, so let's look at some code for this. Okay. So first we have that base case. We return none. Otherwise, I'll say, okay, our data value is going to be that first element of our array, or sorry, not array, our list, and then, sorry, our next is going to be the result of calling linkify with items starting at 1 to the end. So this is list slicing notation, which we've touched on here and there, but haven't been tested on or anything. It's just a shorthand way of like creating a sublist basically, and that's why it was off limits during the list utils exercise 5 that you did. And then we just construct a new list with our data and our next, and that is all. All right, I'm also going to diagram this one really quick because I feel like it is helpful to see. So I'm going to skip globals, and again, I'm not going to show the frames for the node constructor, but if you're being complete about that, you would see the node hashtag init frames on your diagram. So start out with main. The RA is 86, RV, we're not sure, we're not done yet, and we create a list that is the result of calling linkify with 1, 2, and 3. So we don't know what list is yet. So we create one linkify frame, and we have items, which points to, so our stack, or our heap is going to get pretty messy, so I'll try to be small. So points to a list like this. Okay, and we say, or first of all, the RA was 74, RV not sure, and we say, is the length 0? It's not, so we create a variable for our data, which is 1, and our next, which is the result of calling linkify with the sublist from 1 to 2. Okay, so I'm going to create another frame. So then we have another call to linkify. And now items is pointing to a sublist that was all of the elements from our original list, but starting at index 1. Our RA here was 82, RV not sure yet. Our data is 2. Our next is the result of calling linkify again. So we add another linkify frame, linkify, RA 82, RV not sure yet. Items this time is pointing to a little list whose 0th index is 3. So our data is 3. Our next is the result of calling this again. So we call linkify again. RA is 82 again, RV not sure. Now items is just some list with nothing in it. And so now we do hit this base case that the length of our items was none, or 0, so we return none. So the RV here is none. So the RV gets returned to the RA, which was line 82, which was assigning to our next in the previous linkify frame. So that means we jump up to the previous linkify frame and that R next becomes none. So now we finish this frame. Since we left off at line 82, still got to complete line 83, which was returning. So I'm going to use a different color just so it's clear. So it was returning a new node in the data and next. So the data was 3 and the next was none. Okay. And so the RA of this was also 82, which is assigning to our next. So that's in the previous linkify frame. So this our next is pointing here. Okay, so that completes line 82, but now we have to finish this frame because we still have nothing in the RV. It says return another new node. So we create another node with data and next, and the data is 2, and the next points here. And then we return back up to line 82 again, and this our next is pointing here, and then we have to finish off that line 83, which is returning another new node. Sorry for these crazy arrows. So this node has a data and a next, so the data here would be 1, next points here, and this gets returned to line 74, which is assigning to this list variable, and then main is finally done. All right, the next function is scale. So this is back to our normal-ish pattern. If the list we're given is none, return none. Otherwise, make a new node. So we're not modifying the original, we're making a new node with data attribute scaled. Okay. So make a new node with the data attribute scaled, and then keep going. All right, so let's take a look at this in code. All right, so same thing here. We called the parameter head here, but the idea is the same. So if head is none, return none. Otherwise, we want to get the first element of, so let's call it something else. Scaled data is equal to our current data times a factor. Scaled rest is equal to the result of processing this linked list recursively. So we have to go and scale all the rest of our nodes by the same factor, and then go ahead and construct the new, sorry, we cannot type, and then we go ahead and construct the new node. And that is all there is to that one. I definitely recommend diagramming it. All right, so for concat we have several cases. So if both list params none, then we just return none. Otherwise, what if the left list is none, we return a copy of the right. So this means we still have to visit each node and create a copy of it using the node constructor, okay? Otherwise, if right list is none, copy of left. And then number 4 is the case where we still have elements in the left list. So we want to take from left keep going. All right, I think this will definitely make more sense in code, so let's take a look. All right, so first things first, if the left-hand side is none and the right-hand side is none, then we just want to return none, okay? Otherwise, this else statement matches the case where the right-hand side, or sorry, otherwise this else statement matches this case. Let me make a note. This corresponds to left is none, but right is not. Make a copy of right. So what we want to do is get the first right data is just rhs.data. Rest of our right list is the result of calling concat again, leaving the LHS the same because we already know it's none. We don't want to take off, we can't access the next attribute of something that's already none. So we call concat again with its next, okay? And then return the rest. So, oops, sorry. So what this else statement is doing is it's caught you in a situation where there's nothing left on the left. So you just continue on making copies of the right until you run out, and then you hit this return none on line 98. Okay, I definitely recommend diagramming some different scenarios with this one. So otherwise, so if we're at this else, this means left has stuff, so copy it into our new list. So in this case, I'll call this first left data is just the LHS data attribute. The rest of our left list is the result of calling concat, but just moving forward our left list and leaving the right the same. We'll deal with the right up here, right? And then returning that new node with our first left and the rest that we processed recursively with a call to the concat function. Next we have sub. So I'm just going to make a note. So with sub, we're keeping track of two variables, the start. So this is what index we want our new sub linked list to start at, and the length, which is how many nodes we want to include starting at that start index, okay? So the first case we have is nothing super interesting, just again, if the list is none, I don't know, the start is greater than length, or length is 0. All of those cases, we told you to return none. All right, a second case is if the start is greater than 0. So what does this actually mean for us? So if the start is greater than 0, that means we want to keep moving, right? And ignore current node. Because what this is saying is relative to where we are in our linked list, there are still more nodes to go before we want to start. So that's a mouthful, but we can definitely look at this concretely in a second. So if we are making a recursive call here, we would want start to start decreases by 1 for every node we ignore, because we're getting closer and closer to the case where our start is 0. So if start is 0 and the length parameter is greater than 0, what does this mean in English? This means we want to start including nodes, okay? So the length being greater than 0 means we still have more nodes to go to get the complete sublist, and start being 0 means we have no more nodes to go before we want to start. Okay, so with this one, when we move on and make our recursive calls, our length should decrease by 1 now, because as we move forward, we require one fewer node to be added to our list before we're done. Okay, and then, okay, there was one other base case or not base case, but there was another case I probably should have included earlier, but also if the start is 0, we wanted you guys to just adjust by bumping this up, the start index up to 0. So you could have done this, you can do this multiple ways, but I'll just write it here. You can just do sub list 0 length. All right, and then those are the cases that I think are most helpful to start out with. But definitely, this is also just one way to think about it. If you did not think about it this way and your code works, that is totally fine. Nothing wrong with that at all. There's so many different ways to solve these problems, and I'm just showing some solutions in case anyone didn't get a chance to finish or just wanted a peek at how I would have approached it. Okay, so I'm just going to translate what we just wrote into code. So I called the list A. So if the list is none, or the start is greater than or equal to length, or length is 0, return none. Okay, cool. And we also had, then we had that second case. If the start is 0, that means we want to ignore the node that we're currently at. So we are just calling it, we're just calling sub recursively again, but with start moving closer to 0. Because the closer start is to 0, we know the closer we are to the point in which we want to start including nodes for our sublist. Okay. Otherwise, again, if our length is, okay, if the start is 0, this is what we were working towards, and the length is greater than 0, now instead of just ignoring, okay, so actually let me back up. So I'll first say our data is a.data, right? And then our next is the result of calling sub with a.next. Start now stays the same, but length starts to decrease because with each new node we construct, the length required to complete the sublist decreases. So now instead of returning, like, okay, so now we want to actually return this node, right? Because once we are in this case where the start is down to 0 and our length is greater than 0, add things to sublist. Sorry, and in this case, ignore and get to start. And get, okay, I should word that better. So ignore and advance to position where we want to start. So here we return our data, our next. Okay. Oops, sorry. Cool. So lastly, we had that fourth case where we can just return A with the index bumped up to 0, gives A and length unchanged. All right. And we know we know implicitly, right, that if it reaches this point, then that start must have been less than 0. All right, again, I'm going to do a diagram for this little example. So I am going to skip globals just for simplicity's sake. The return address for main is 131 RV, we don't know yet, and sublist, we also don't know yet, but we do know that passed in as a parameter to our call to sub was some linked list that had to be constructed. So I am just going to go ahead and just construct this on the heap without doing the constructor frames, but that is always a good exercise to do. So the data was 4 and none for the first node, and then we had 3 in that node, and then node D2, node D1. Okay, so that's the linked list that we pass in as a parameter to our recursive sub function. So we call sub, the RA was 112, RV, we're not sure, but we know we have this A parameter that starts out pointing to the start of our list here. Start is index 1, and length is 2. So what we're trying to get at the end of our endeavor here is we're just trying to get a list with just 2 and 3 in it, starting at index 1 and length of 2. Okay, so we check these conditions, none of them are true. Our start, however, is greater than 0, so we're going to ignore this one node. So what do? We call sub again, but this time we return, or we were called from line 121, RV we don't know. Now A is pointed here, and our start has been reduced to 0, length unchanged. So now we reach this condition on line 122, and so we set up our data to be 2, and our next, we have to go compute by calling sub again. So if we do that, now our RA was 125, RV we don't know. We called it with the previous A's next attribute, so our A is here now. Start remained unchanged. Length, however, went down by 1. So length should be 1. Okay. Our data is 3. Our next, we don't know yet. So we go ahead and call sub again, and I'm gonna do this last subframe off to the side because I ran out of room. I apologize. So RA 126 or 125 again. RV, don't know. A is now pointing here. Start is 0 and length is 0, since in our recursive call from the previous frame we had length and we called sub with length -1, so it's 0 in this subsequent frame. So now we hit the base case with length equals 0 and we return none. So the return address was 125, which was assigning to our next in the previous frame. So this our next becomes none, okay? And so then we finish line 25, now we need to complete the frame or the function call with 126, which constructs a new node. So remember, we're all about the copies here. We don't want to just use the one we were given. A new node with the data held in our data, which is 3, and the next, that is the value of our next, which is just none. Okay, and then we return that from this subframe. So our RV here is this, And this sub function call returns back to line 125 again, which is also assigning to our next in the previous subframe. So this our next is pointing here. And so we're done with that line. And so then on line 126, we construct a new node to return. So let's draw that in here. So its data takes on 2 and n points here, and that is what we return. Okay, this takes us back to line 121, which was this sub call where we were not constructing any new nodes. So we just have the same list as our RV. And then this returns to line 112, and that was up in main. So sublist just ends up pointing to this new mini linked list we've made that just has 2 and 3 in it. All right, I actually think sub is the hardest function. So now we've tackled that. So now splice should be a walk in the park, right? So I'm kidding, but it's definitely hard, and you all should be very proud of yourself of how hard you've worked all semester and on this exercise. But for splice, we're gonna have just a reminder of the parameters. We have list 1, an index, and list 2. And the idea is if you had something that was like splice 1, 2 at index 1, you wanted to splice in 3, 4, your result list would be something like 1, or it would be 1, 3, 4, 2. Okay. Cool. So now that just a quick refresher on that, let's just go over the cases that we're going to code up. So, okay, if both none, return none. Okay. If list 1 is none, copy of list 2, and then vice versa. If list 2 is none, sorry for my writing, copy of 1. Okay, and then another, I guess this is a base case, even though it's going to result in recursion, but in another function. Okay, so if our index is less than 0, or less than or equal to 0, what we really want to do is just concat list 2 onto the front of list 1. Okay, cool. Otherwise, this is our recursive case here. We want to keep, or I guess we have more than one recursive case, right? This is recursive, this is recursive, this is recursive, but the one that has more of this fun stuff happening. So we want to keep elements of list 1 and keep moving. And what do we want to keep moving towards? We want to keep moving towards the point where our index is 0 or less than or equal to 0. So, because that means we're getting closer and closer to the point where we want to splice in our second list. Okay, so this is index will be decreasing by 1 each time. So let's look at some code. All right, so first of all, if A is none and B is none, return none. Otherwise, if A is none, then we want to return a new node where the data is B's data element, or data attribute, and the next attribute of our new node is the result of continuing to call splice with A unchanged, since we know it's none already, index unchanged, and B advanced 1. Okay? Otherwise, if B is none, then same idea, we want to create a new node where we keep A's data, but then the next attribute of our node is the result of calling this function again, advancing A forward and leaving the rest unchanged. Sorry. Okay. And then we have another elif. Our index is less than 0, or less than or equal to 0. We just want to return B concatenated in front of A. Okay, so for example, if we were calling splice of 1 to 0, 3, we would want our result to be 3, 1, 2. So that's why we have this case here. All right, and then last but not least, our final case is that we want to return a node. Oops, sorry. Return a new node with A's data. So we're down here if neither are none. So we need to add on elements from A until we get to the index where we want to do the splicing. Okay, so our data that we're adding to the new list is just A's data, and then the rest we have to go calculate recursively. So we advance A, we reduce the index to get closer to this case here where we stick B in front of A, and then leave B unchanged for now. So I think it will be useful. I will not diagram this one. I will leave that as a fun exercise, but I will still trace through it with an example because I think that will be helpful. So let's see. So if, for example, let's try this with splice 1, 2. So it does, every list ends with none. Our index is 1, and the result is 3, 4. Or our index is 1, and our second list is 3, 4, none. So the first time we call splice, none of these are true, so we hit this case. So what do? We return a new node where the data is just 1, but we call splice recursively again with 2 none. Now the index is 0, and B is unchanged. Okay, so now we hit this case here where index is less than or equal to 0. So this splice calls concat of 3, 4, none, and 2 none, which returns a list that looks like this: 3, 4, 2, none. Okay, and that gets returned back up here to our node that we were trying to construct. So what we have left here is a list that is 1, 3, 4, 2, none, and then that gets returned back up to be the result of this splice call, which is what we would expect if we're splicing 3, 4 into the first index of our 1, 2 input list. All right, I hope this helped a little bit. And again, you definitely did not have to have your solutions looking just like this. I hope I didn't go too fast, but please feel free to go back, slow down, or rewatch, or email me with any last minute questions before the exam tomorrow. You all will do great.